First of all, I would like to thank the organizers for everything, for being here, for giving me the opportunity to give a talk, and also for last night, which was great. I'm going to talk about case-sum-free subsets. So before introducing the real subject, I will explain on an example what I am interested in. So if you, for example, if you look at sum-free sets in the integers less than n, you have two kinds of maximal sets, meaning sets having as many integers in it as you can. The first one are of the form n divided by 2n, because if you add two numbers strictly larger than n over 2, then obviously it's larger than n, so you're not in this set. And the other kind is odd numbers. So I should say that the first kind is a combinatorial kind of maximal set, and the second one is arithmetical kind of such set, such maximal set. And I will be interested in these sets. Actually, these sets come from the continuous setting also. I mean, it works the same in the continuous setting. If you're looking for maximal sum-free sets in the interval 0, 1, so you look for A included in 0, 1, such that A plus A and A has intersection 3, then you can take 1 over 2, 1. And this is a maximal set. The density 1/2 is the maximal you can hope. The measure here is the maximal density you can hope. So that's one of the motivations to study K-sum-free subsets. Just look in 0, 1 in the continuous setting, because if you have some maximal sets in the continuous setting, you can get some sets with no solution in the discrete setting. So I will be interested in K-sum-free subsets, meaning that I will take K and a real number larger than 2, and I will say that A included in 0, 1 is K-sum-free if there is no solution of the equation x plus y equal kz in A. Okay, and I will look for the maximal size of such a set. Sorry, different. Thank you. Okay, so before going to the size, I have to define the size. And I will take for the size the inner Lebesque measure, meaning that I take the supremum of the Lebesque measure of B for B a closed subset of A. Okay, so that I don't have to look if the sets are measurable or not, if the sum is measurable or not, and all this stuff. So this problem was studied by Chung and Graham, who proved in 1996 that for k larger than 4, so they did that for integers only, but it works exactly the same if you take a real number larger than 4. So the maximal size, which I will write lambda k, so that the supremum of A such that A is a subset of 0, 1, and A is K-sum-free. So they prove that lambda k is equal to 1 minus 2 over k times k squared minus 4 divided by k 4 minus 2 k squared minus 4. So they proved that, and actually they also gave a description of maximal sets, meaning sets having the maximal size, k sum free, and maximal in the sense of inclusion. Okay? And they say that this set, gk, maximal set, is given by the greedy algorithm, and I will describe what this set is later on. So it's the union of free intervals given by the greedy algorithm. And as a motivation, it allowed later Batz, I have to see, there are many of them. So Batz, Egarty, Knappe, Larsson, and Schoen. In 2005, they proved that you have the similar thing in the discrete setting, meaning that if you are looking for maximal sets in integers less than n, then they are exactly what you obtain by multiplying that by n. And the density is this lambda k, the maximal density. Okay, so I will explain how you get this set, what this set looks like, and I will also explain how you get the lambda k, which is a consequence of getting gk. And we will also see what happens for k equal to 3. For k equal 3, actually, there's a difference between the continuous and the discrete setting. Because in the discrete setting, you have odd numbers. Obviously, you don't have any solution to x plus y equal 3z in odd numbers. So it has density 1/2. Whereas Chung and Graham conjectured that in the continuous setting, you get lambda 3 equal to 77 divided by 177, which is less than 1/2. And this lambda 3 is actually given by this formula taking k equal 3. Okay, so that was a conjecture made in 86 also. And it took us a long time to prove this conjecture. So there was the first result by Matolci and Ruja. Is it the other way? Yeah, sorry. So I guess it's 2005 or 4? 9. Make it 9. Okay. Proving that lambda 3 is less than 28 divided by 57, which is less than 1/2. So it was proving that there was a difference between the discrete and the continuous setting for k equal 3. And actually with Alain Plagne, we proved the conjecture in, so it will appear soon, hopefully. So we put that on the archive last year, I guess, so I will give this date. That lambda 3 is 77 divided by 177, and that the maximal set with solution in the continuous setting is given by the greedy algorithm also. And we are now working on k.
Maybe it should be k to 4 in the result.
You mean describing?
Maybe k to 4 minus 4.
Oh, yeah, you're right. Genau, yeah. Thank you. Actually, we are now studying the case k between 2 and 3. Since we're working with real numbers, we don't care if k is entire or not, I mean, an integer or not. If I have time, I will also talk about this case, where we have the greedy algorithm at the beginning, if k is not too far from 3, and then there's something else which is better than the greedy algorithm. So first, let's explain what happens for k larger than 4. So first you can, if you have a maximal set with no solution, then you may assume that the supremum of A is 1. If not, you delay to set and you get something which has bigger measures. So, okay, so you take the maximal here, and then you will use the greedy algorithm, meaning that you will eat whatever you can until someone tells you, no, you can't now. Okay, that's the principle. So I begin in 1 and I just eat until there's an obstruction. An obstruction being a solution to the equation x plus y equal kz. Okay? And if I take x and y less than 1, then x plus y divided by k is obviously less than 2 over k, so I can take everything until 2 over k. Okay? That's the first interval. Okay, then if you take all of that, you cannot take elements which can be written as x plus y divided by k for x and y between 2 over k and 1. So you cannot take what is between k over 4 divided by k squared and 2 over k. This is... And now if you know that the infinimum of your set A is here, let's call it A, then you cannot take what is between A plus 2 over k divided by k and A plus 1 divided by k. And the good thing is that for k larger than 4, so here we will have 2 over k plus a divided by k. Okay, I will write a plus I1 divided by k. Okay. And the good thing is that this point, 1 plus k, 1 plus a over k, sorry, is larger than this one when k is larger than 4. So for k larger than 4, these two intervals overlap. And so you have nothing between the two of them. So you cannot begin to eat again until you reach this point, which is a plus 2 over k divided by k. And now, once you reach that, A1 has no influence anymore, because you took the smallest element of A1, the smallest element of the set, and it's on the right. So you can continue again, and so you will eat everything until you reach 2 over k times b, where b is this point. And again, you will have this interval where you cannot take anything, and you do it again. And you choose a, so that this point is k divided by 2 times a. And this point is this one, is this one plus a divided by k. And it gives the set gk. Okay, so for k larger than 4, it's not very hard to see how it works. What is harder is to prove that this is actually the maximal set. And the thing is that we may not take all of this interval. But if we only take part of it, let's say A1, then here we will have a forbidden set which is A1 plus A1 divided by k. And so if A1 is of size 1 minus 2 divided by k, that's the maximal size minus epsilon, then here A intersected with this interval cannot be larger than 2 epsilon over k. because you have to take the size of this interval, which is 2 over k times the size of this one, and you have to erase the size of this set, which is at least 2 epsilon over k. No, sorry, 2a1 over k. Okay, so here we will have A intersected with this set, which is less than 2 epsilon over k. And if you look at this interval here, then that's the same. You will have A plus A1 divided by k, which is a forbidden set. And so you cannot have more than the size of the whole interval minus the size of A plus A1 divided by k. It means that here you cannot have more. I mean, the intersection of A with this interval cannot have size larger than epsilon divided by k. So here. And so you have at most 2 epsilon divided by k here, epsilon divided by k here, so it's 3 epsilon divided by k. And since k is larger than 4, you have a measure on this interval, which is less, which is smaller than what you could have if epsilon is equal to 0. Okay? So it means that A intersected with B1 will be less than what you can have with epsilon equals 0 times, so that's a 3. And so it means that if you want to have the largest set possible, you have to take all of A1 and the same for the following ones. Okay? So this was for k larger than 4. And now the question is, why doesn't it work as well for k equals 3? Oops. So for k equals 3, you do the same as greedy algorithm. Take whatever you can. Sorry? Ah, pardon. Okay. It's too small. Okay, I will try that. Okay. It's still too small? Okay. It's okay, it's okay. Okay, so here you have 2 divided by k. I will keep k, but k is equal to 3, but it also works for k between 3 and 4. That's why okay. So you take everything here, and so you cannot take, so that's I1. You cannot take what is between 2 over k, so 4 over k squared, and 2 over k. For intervals, that's the same, but okay. And you cannot take either what is between A plus 2 over k divided by k, and A plus 1 divided by k. But now you may have room between the 2 intervals. And so you have to say what happens if we have some elements of A here. Can we eat something here, or do we have to wait until here to be able to eat again? And actually, we cannot take anything here. Let's say that you have C here, which is the infimum of B, B being the set of A intersected with this interval. So that's what is here. Okay? Now, we will see that B is a subset. I mean, it's, yeah. Okay, we will see that this interval here this one, is actually included in C plus I1 divided by K. Why is it so? Just if you want C plus 2 over K divided by K to be larger, to be smaller than C, it means that C, so C is larger than larger than 2 divided by K, K minus 1. And since C is larger than 1 over K, for K larger than 3, this is true. Okay? And now we want 4 over K squared to be less than C plus 1 over K. So it means that C is larger than 4 over K minus 1. And this is also implied by the fact that C is larger than 1 over K if K is larger than 3. So it means that here you have C plus I1 divided by K, which is forbidden. If you took all of this interval, you cannot take that, because C is an element of A, or at least it's not necessarily closed, but if it's not an element, then you can find a sequence which tends to it, and it works also. Okay, so that's the reason why the greedy algorithm gives the same set GK as before. And now it's harder to prove that this set is actually a maximal set, and you cannot do better than that. Because if you take here everything, so you have A1, and you take A1 so that the size of A1 is 1 minus 2 divided by K minus epsilon. So you take everything except epsilon. If you do exactly the same thing as here, you get a possible set of measure 2 epsilon divided by K here, epsilon divided by K here, and epsilon divided by K here. And so you have 4 epsilon divided by K, and K is only between 3 and 4, so it doesn't work. Okay, so you have to do something else. The first thing is to use, instead of using the Cauchy-Davenport inequality, we can use something better, which is due to Rouja. He proved that if you take a set B of real numbers, then the size of B plus B, the size being the inner Lebesque measure, is at least the minimum of the size of B plus its diameter and 3 times the size of B. Okay? So let's say that, okay, so we want to apply that to A1. Okay? The first thing is to say that actually we will take this lower bound, just because if we want A to be large enough, A1 cannot be too small. So epsilon cannot be too large. This is a lemma which was already in Matolchi and Rouja's work. And it's just because if you look at A1 plus A1 divided by K, this is a subset of this interval here, and A intersected with this subset there's no intersection between A and this subset, and so it gives that A1 has to be large enough. So it means that actually we can use that. And let's say for simplicity that the diameter is 1 minus 2 over K, meaning that 2 over K is in the set or very close to elements to the set. Then we gain a 2 here, and we have epsilon over K. Okay? So actually this is not always true. You have to deal with this diameter thing. It may be that your set only begins here, but if you're careful enough, you can deal with it. So I won't talk about this technical thing. And so you have epsilon over k, epsilon over k, epsilon over k, 3 epsilon over k, and if k is at least 3, we have the same thing. And now you have to deal with the equality case. I'm just saying that if you have exactly equality, actually you did that with C, but with another element of the set which is very close to C. You can also do that, and if you have equality, everything has to fit exactly, and you can translate it a little bit, and it has to fit with the other one, and it's not possible. Okay, so that's how you find GK and say, okay, GK must be the maximal set. And you can prove that also. Okay, it's technical, but it works well. And now maybe I have 1 minute, 2 minutes, 3 minutes. Oh, great. So I can talk a little bit about what happens for k between 2 and 3. Actually, so this work is, I should have written that. This is a work in progress, and this is a joint work with Alain Plagne and Bruno Pinson, who did the numerical experiment. So we had to use computers. And what we see is that the greedy algorithm and the set GK, it seems to be the maximal set for k larger than 2.4. Well, I have to look at it. I can't remember. 4278 something. Okay, so it looks like for that we have GK, which is the maximal set, and then lambda k, which is the maximal size. And then it changed. What is funny is that it seems that it does not change from 3 intervals to maybe 4, but from 3 to 6. And what I will just try to explain is why. Well, why doesn't it change at the beginning? So you always take all of that, and you have to raise 2ik divided 2i1 divided by k. You have to raise a plus i1 divided by k, a being the smallest element here. And you have room between the two of them, but you can use that if A has no solution to the equation x plus y equal kz, then A intersected with A divided by k minus 1 must be empty. Okay? Just because if you have you take that, and so x is equal to 1 over k minus 1 y. Okay? So it means that here you must also exclude I1 divided by k minus 1. Okay? But still, there may be some room. But if k is close enough to 3, and if you take, say, an element x in A, then you must exclude xk, kx. So if x is in A, then kx minus I1 is intersection 3 with A. Okay, because if you take an element of I1, sorry, this is an element of A, and so you will have that kx minus y is equal to z, and that's a solution to the forbidden equation. So it means that this is This is a long set. This has size at least 1 minus 2 over k, which is large if k is not too close to 2. And you have to exclude it. So most of the time you have this huge set here. And if you take only one element, you have to erase all of that, meaning that you lose a lot. And so if k is close enough to 3, you lose too much doing that. So that's not worth. You'd better not take anything here and begin here. On the contrary, if k is small enough, then it begins to be interesting to take some interval here. And so you take one more interval here. You have to erase all of that. So you begin again here. And you have 3 more intervals which appear. And the 3 smallest intervals are actually a contraction of the greedy algorithm interval set. So, yeah. So there are still many questions. I will just finish with the questions. Sorry. We don't know if lambda k is a continuous function of k for k close to 2. We don't know even if it's an increasing function of k. We think so, but we don't know. And mostly we don't know what the shape of the maximal sets are, meaning do we have more and more intervals if we come to 2? It looks like yes, but there may be some kind of phases where you have a stable number of intervals, and between one phases to the other, maybe we may have an infinite number of intervals. We don't know. So plenty of work. So thank you.
So thank you very much for this great talk. Are there any questions? Yes?
Please look at me. What happens when k is very close to 2, just larger than 2? Because when k equals 2, then you have just 1 interval, right?
What we know is that if k is smaller than that, then the greedy algorithm is, I mean, with the 3 intervals, it's not anymore the best one.
I understand, but
and
did you do any numerics for k equals
2.001? We did, but the problem is that we can only test with 7 intervals because of the numerical problems. And so I guess that there are more and more intervals, but I couldn't prove anything. We couldn't prove anything on that.
Other questions? Yes?
What happens if you consider the problem modulo 1?
Actually, that's a very good question, and I know some people who are interested in that. It's not as easy because of, the computations are even more messy. But that's a good question. That's something interesting.
So do we have further questions or comments for the speaker?
That's one here.
Yeah. Just to clarify, in the very beginning of your talk, k was whole numbers, right? Really? Integers.
Integers.
Yeah. And in the end, k is real.
Actually, what was done for k integers larger than 4 works for any real number larger than 4. What was done for k equals 3 worked for k between 3 and 4. And then
so that formula works for not integers only.
Yes.
So why are you asking? We don't know lambda k is. I don't know nothing about lambda k. If you've got a formula
we know that for
that.
k larger than 3. But for k close to 2, we don't know how it behaves.
I see.
Further questions? Well, if not, let's thank the speaker again. And he's so next talk in 2 minutes.